Hello everyone. Today I'd like to introduce a system which using transfer learning to select the best VM for big data applications across multiple frameworks. We are from ISCAS, UCAS, and SKLCS. So big data applications running on clouds are very popular today. There are numerous applications from dozens of frameworks such as Hadoop, Spark, Flink, and etc. Cloud providers such as Amazon EC2, Alibaba ECS, and Microsoft Azure provide virtual machines as the basic runtime environment for those big data applications. If you want to run a big data application, you should configure the VM first. However, there are dozens of big data frameworks out there, and cloud providers offer hundreds of VM types as well. This combination makes things more complicated. That is to say, for any application and its framework, it is a big challenge to select the best VM to achieve better performance and lower budget. Existing machine learning solutions usually connect low-level metrics, for example CPU utilization data, to help them train models for various big data applications. However, the way of reusing pre-trained model may cause high prediction error for new frameworks because their low-level metrics are completely different. So, what if we train models for each framework separately? The answer is the training overhead is also unacceptable. It may take hundreds of hours to collect data for each framework. So the problem of machine learning-based system is it either has high prediction error or spends heavy training overhead. This will cause poor application performance for users and additional budget for cloud providers. The question is how to balance prediction error and training overhead for multiple big data frameworks. So in our article, we introduce a lower transfer learning-based solution, Vesta, to select the best VM across multiple big data frameworks. We first abstract knowledge from source frameworks to train a prediction model. After that, we update the model for new frameworks incrementally with the help of transfer learning techniques in order to minimize prediction error and training overhead. Our core finding is the knowledge across frameworks. We've observed that low-level metrics have high-level similarities across frameworks. From the heat maps, we can see the blue areas represent that these cross-framework applications have similar CPU and RAM requirements. Based on these observations, we first abstract knowledge by a large-scale evaluation. We choose 3 most widely used big data frameworks and 30 benchmarks workloads from HighBench and Big Data Bench, and run them on 120 VM types on Amazon EC2. After each test run, we collect 20 resource and execution metrics, such as CPU rate, number of tasks, and etc. After that, we analyze correlations for those metrics and evaluate which correlation could become knowledge across frameworks. We evaluate top 10 valuable knowledge across frameworks based on current dataset. To be more specific, we analyze the data distribution by leveraging a scoring mechanism. As shown in the graph, we use number of workloads in the x-axis to evaluate the popularity of knowledge, and use workload consistency on VM type in the y-axis to measure the similarity. Thus, we can get valuable knowledge across frameworks through a large dataset. Then, we train a k-means model for source frameworks. After that, we represent knowledge in a two-layer bipartite graph. As we can see, this graph can represent the relationship among workloads, labels, and VM types. The blue boxes and edges are from source frameworks, and the red boxes and edges are from target frameworks. From the bipartite graph, we are able to share and reuse knowledge across frameworks. Then we would like to introduce how do we reuse knowledge. We first decompose the bipartite graph into different matrices. These matrices include workload label relationship and label VM relationship. However, because of the target workloads just enter the system and lack of data, they have data sparsity problem. The next step, we solve the data sparsity problem by applying a CMF algorithm. After that, we search the best VM for target workloads and frameworks by employing a SGD algorithm. Finally, we train the model incrementally for target workloads. We do some evaluations on EC2 using 3 frameworks and 30 workloads. We treat Hadoop and Hive as source frameworks and use Spark to simulate target framework. We compare with machine learning solution Paris and performance modeling solution Ernest. The metrics include performance improvement, which evaluated by prediction error, training overhead, which evaluated by number of runs, and practical metrics, which evaluated by execution time and budget. As we can see in the result from different workloads and frameworks, our system achieves 51% lower prediction error. That is to say, we can improve up to 51% application performance. We further investigate the improvement of training overhead on multiple frameworks. The result shows that our system can reduce up to 85% training overhead because of transfer learning techniques we used. We also test our system in practical applications to optimize the execution time for them. The result shows that our system can find VMs with shorter execution time in 5 of 6 applications. We also evaluate the budget of renting VMs. As we can see, our system performs better or at least comparable budgets comparing with other solutions. So, in conclusion, we build a transfer learning-based system to select the best VM for multiple big data frameworks. With the combination of various novel techniques, our system can select the best VM across frameworks accurately and effectively. Our system can easily adapt to big data frameworks with BSP design. In the future, we want to extend our system to support deep learning applications in TensorFlow and PyTorch. Please take a look of our paper for more details. Okay, that's all for my representation. Thank you for your listening.